Welcome to section 3.7, Polynomial and Rational Inequalities. All right, objective number 1. Solving a polynomial inequalities, or solving polynomial inequalities. So in our first example, we're asked to solve this polynomial inequality using a graph. So we need to solve the quantity x plus 4 times the quantity x minus 3 squared is greater than 0 by graphing f of x equals x plus 4, that quantity times x minus 3 squared. So whenever you're given a polynomial inequality like this, the first thing that you want to do is graph the side that contains your polynomial. So first, this polynomial is set to 0. All right, so we want to graph the polynomial side, which we have here on our screen to the right. And then from that, we want to identify any key information that we see. So we have certain values. We see here that we have an end behavior that is representative of y equals x cubed. And then from this, we then can determine certain things. So let me write this out. So for number 1, in order to solve this, we want to graph f of x equals x plus 4 times x minus 3 squared. Then for step number 2, we are going to determine the intervals. Okay, so we're going to determine the intervals of x when the graph is above the x-axis. Now, why are we doing this? Well, it says here that our inequality is greater than 0. So any values that are going to be greater than 0 are going to be above the x-axis. Okay, so f of x is greater than 0 for all values of x between -4 and 3, or x is greater than 3. Okay, because at the point 3, we lie on the x-axis and we want everything greater than 0. So 3 in itself cannot be a solution. Okay, so we then can write out our answer either in solution, as a solution set, or as interval notation. So as a solution set, it would look something like all x values where x is greater than -4, less than 3, or x is greater than 3. So that's how you would write it as a solution set. In interval notation, you would write it parentheses -4, 3, union 3 to infinity. Okay, and that would be the solution to our inequality. Okay, so the results of this previous problem we just did is leads to the following approach to solving polynomial and rational inequalities algebraically. So suppose that the polynomial or rational inequality is in one of these forms. So you could have f of x is less than 0, greater than 0, less than or equal to 0, greater than or equal to 0. You want to locate the real zeros of f if f is a polynomial function, and then locate the real zeros of the numerator and denominator if f is a rational function. Then we're going to use the zeros to divide the number line into intervals, because on each interval, the graph of f is either above the x-axis, where f of x is greater than 0, or below the x-axis, where f of x is less than 0. And then this will enable us to identify the solution of the inequality. So in our example here, we're asked to solve x to the fifth is greater than negative x squared algebraically, and then graph the solution set. So for step number 1, we're asked to write the inequality so that a polynomial function f is on the left and 0 is on the right. So we're going to start off with what they gave us, which is x to the fifth is greater than negative x squared. We're then going to add negative x squared, add x squared, to both sides, but we want to move this term to the left-hand side. So we'll get x to the fifth plus x squared is greater than 0. Okay, so now we have our polynomial on the left-hand side and 0 on the right-hand side. Now for step 2, we want to determine the real zeros, which are the x-intercepts of our graph of f. Okay, so we have f of x equals x to the fifth plus x squared, and we're going to set this equal to 0 to find our x-intercepts. So writing this in factored form, we'll have x squared times x cubed plus 1 equals 0. Okay, now we can factor this further by x squared times x plus 1 times x squared minus x plus 1 equals 0. So setting each of our factors to 0, we'll have x squared equals 0, x plus 1 equals 0, and x squared minus x plus 1 equals 0. So this will be x equals 0, this will be x equals negative 1, and x squared minus x plus 1 is not factorable, so this has no real solutions. Okay, so it gives us imaginary solutions, but no real solutions. So then we know that our x-intercepts are going to be the points 0, 0, and negative 1, 0. So those are the two x-intercepts. Okay. Alrighty. Now for step 3, we're asked to use the real zeros that we found in step 2 to divide the real number line into intervals. Okay, so our real zeros that we have are negative 1 and 0. So our intervals are going to be from negative infinity to negative 1, from negative 1 to 0, and from 0 to infinity, which then leads us into step number 4. So we can now select a number in each of those intervals, evaluate f at that number, determine whether the value of f is positive or negative. If the value of f is positive, then all values of f in the interval are positive. If the value of f is negative, all values of f in the interval are negative. Okay, so our first interval is going to be from negative infinity to negative 1, then negative 1 to 0, and then 0 to infinity. We can choose a number in each of these intervals. So I'm going to choose negative 2, let's do negative 0.5, and 1. So we'll evaluate f at each of these values. So f of negative 2, f of negative 0.5, and f of 1. And we can utilize our calculator to help us. All right, so now we're going to go to y equals, and we're going to enter in our function. And our function is x to the fifth power plus x squared, because we want the values of y. We'll enter that in. We'll go second graph to go to our table, and we want the values of negative 2, we want negative 0.5, and we want 1. If your calculator is not going by 0.5s already, you'll need to reset the change in your table. So you'll go second window to go to table set and change your table difference to 0.5. So when you go to your table, you're now going by 0.5s. All right, so we need negative 2, which is negative 28, we need negative 0.5, which is 0.2, and we need 1, which is 2. Okay, so let's write that down. So we have negative 28, we have 0.2, and we have 2. So we'll have the point negative 2, negative 28, negative 0.5, 0.2, and 1, 2. Okay. Our first point, the y is negative, so this will be below the x-axis. And our last two have positive y values, so both of them will be above the x-axis. So above the x-axis. Okay. So on our axis here, our x-axis, let's plot our 0. So that's negative 1 and 0. And we are looking at a polynomial that needs to be greater than 0. So our solutions are going to be from negative 1 to infinity. Okay. Now we can't equal, x can't equal negative 1 because negative 1 is a 0 and our polynomial has to be greater than 0. So we'll have a parentheses. Sometimes you might see an open circle and an arrow depending on what your textbook states. Okay, so f of x is greater than 0 for all numbers x for which x is greater than negative 1. So as a solution set, it will be written as x, where x is greater than negative 1. And as interval notation, it'll be from negative 1 to infinity. Awesome. So in our previous example, because negative 1 is a 0 of odd multiplicity, because x plus 1 is a factor to the first power, the sign of f changes on either side of negative 1. However, because 0 is a 0 of even multiplicity, so x is a factor to the second power, the sign of f does not change from one side of 0 to the other. So in our equation here, let's go back. All right, when we factored and we got our x squared right here, our x squared and our x plus 1 factors, we see x squared has a power of 2, meaning it has an even multiplicity, and our x plus 1 has a power of 1, which is an odd multiplicity. So since it's odd, the sign of f changes on either side of negative 1. So if we look here at our table, right, one side it's below x-axis, the other side it's above the x-axis. And since 0 is even, we are on the same side, meaning at 0 we just touch the x-axis, whereas in negative 1 we actually cross it. All right, objective 2, solve rational inequalities. Okay, so we just looked at polynomial inequalities, and so now we're going to look at a rational function inequality. Okay, but it's very similar steps. It's just take into consideration the fact that you have a polynomial in the numerator and a polynomial in the denominator. Okay, so let's first look at our graph, identify the areas in which we're trying to solve our inequality in order to find our solution. Okay, so here is our graph for x minus 1 divided by x squared minus 9. Okay, and we want a solution where r of x is greater than or equal to 0. Okay, so greater than or equal to 0 is going to mean that our solutions are going to exist above the x-axis, but they could also exist on the x-axis. So that's going to be this whole top part of our graph. Okay, so now what values of x provide us those solutions? So that's going to be when x is greater than -3, but less than or equal to 1, or when x is greater than 3. All right, so as a solution set, we would write it as all x values where x is greater than -3, but less than or equal to 1, or x is greater than 3. All right. And then for interval notation, we would write it as parentheses -3 to 1 bracket union 3 to infinity. Alrighty. So we can also note that between 1 and 3, our graph is below the x-axis. So it is not included in our solution. Okay. Awesome. So to solve a rational inequality algebraically, we follow the same approach that we use to solve a polynomial inequality algebraically. However, in addition to finding the real zeros of the rational function, we must also identify the real zeros of the denominator, which is at the bottom of the rational function, because the sign of a rational function may also change on either side of a vertical asymptote. Okay, so it's the same similar approach as we did with polynomial inequalities, but we also have to consider the zeros of the denominator specifically. Okay, so let's do an example. So here we have our rational inequality 2x squared plus 5x plus 6 divided by the quantity x plus 1 squared, which is greater than or equal to 2. And we're asked to solve this algebraically and graph the solution set. So for step number 1, we need to write the inequality so that our rational function f is on the left side and 0 is on the right side. So we'll start with our 2x squared plus 5x plus 6 divided by the quantity x plus 1 squared greater than or equal to 2. So we're going to subtract 2 to the left side so that we can have that 0 on the right-hand side. Okay, so you always want 0. Before even solving for any solution, you always want 0 on one side of your inequality. So now to simplify the left-hand side, we can make common denominators. So we can multiply the term -2 by the denominator, x plus 1 squared. So that's 2x squared plus 5x plus 6 minus 2 times x plus 1 squared all over x plus 1 squared greater than or equal to 0. Okay, so now we can simplify the numerator. So we'll have 2x squared plus 5x plus 6 minus 2 times x squared plus 2x plus 1 is greater than or equal to 0. So all of this is under x plus 1 squared. Then we can distribute the 2. So we'll have -2x squared minus 4x minus 2. And then we can combine like terms. So the 2x and the -2x squared, those cancel. We have 5x minus 4x, which is x, 6 minus 2, which is a positive 4, over x plus 1 squared is greater than or equal to 0. Okay. And so that is our inequality where our left side has our rational function and our right side has 0. All right. Step 2, we need to determine the real 0, so the x-intercepts of the graph of f, and the real zeros for which f is defined. Okay, so note that we found f to be x plus 4 divided by x plus 1 squared. Okay, so to find the x-intercepts, we're going to set our numerator equal to 0. So x plus 4 equals 0. So x equals negative 4. All right. And then we are going to write that as an ordered pair. So that's going to be negative 4, 0. So that's our x-intercept. Okay. So negative 4 is a real 0. Now we need to find where f is undefined. So that's going to be our vertical asymptotes. So that's where we set our denominator equal to 0. So that's going to be x equals negative 1. So this is our vertical asymptote, but it also tells us that f is undefined at x equals negative 1. Okay. So now we're going to use the real zeros and the undefined values that we found in step 2 to divide the real number line into intervals. So we have negative 4 and we have negative 1. So our intervals are going to be negative infinity to negative 4. Then we'll have negative 4 to negative 1 and negative 1 to infinity. Okay. So let's now complete step 4, where we will select a number in each of these intervals, evaluate f at the number, and determine whether f is positive or negative. If the value of f is positive, then all values of f in the interval are positive. If the value of f is negative, then all values of f in the interval are negative. So we know our 3 intervals. We have negative infinity to negative 4. We have negative 4 to negative 1, and we have negative 1 to infinity. The numbers I'm going to choose will be negative 5, negative 2, and let's just do 0. So we'll evaluate f at negative 5, evaluate f at negative 2, and evaluate f at 0. Okay, so we'll grab our calculator to help us, and we'll go to y equals, we'll clear this out, we'll enter in our f of x. So we have x plus 4 in the numerator, and then we have the quantity x plus 1 squared in the denominator. Then we'll second graph to go to our table, and we need the y's for negative 5, which is right here. We need the values for 2, or negative 2, which is 2, and we need the values for 0. And you could have chosen another number, which is totally fine. So 0 is 4. So we could have chose 0.5, which is 2. So we can change that as well. Since we kind of already know 0, let's change that to 0.5. So 0.5 is 2. All right, and I already identified 0.06. All right. And then I'll change 5, and this is 2, and negative 2 is 2. So this gives us the point negative 5, comma, negative 0.06, negative 2 and 2, and 0.5 and 2. Okay. Now, where is their location on our graph? Well, since the y here in our first point is negative, this is going to be below the x-axis. Our next point is going to be above the x-axis. And our last point here is also going to be above the x-axis. Okay? And that makes complete sense because we know the factor that got us -1 as a undefined 0 has a multiplicity of 2. So we know that on both sides of this 0 in quotation marks, we're going to be on the same side, whereas the factor that got us our 0, -4, has a factor of 1, which is odd. So we're going to have our graph be on different sides at that 0. Okay. So for our inequality, we want all of the x values that are greater than or equal to 0. Okay. So we know our values are going to be greater than or equal to 0, starting at -4 all the way to infinity. But we have some restrictions. So -4 we know is a 0. So if we plug in -4, we'll get 0. So x can equal -4, but x cannot equal -1. So we would place an x there. Sometimes you'll see this as a dot, and then you would see a hole at -1, and then an arrow, again, depending on what your textbook states. So f of x is greater than or equal to 0 for all numbers x, for which x is greater than or equal to -4, but less than -1, or x is greater than -1. Okay. As a solution set, we would write it similarly. All values of x, where x is greater than or equal to x, less than -1, or x is greater than -1. And in interval notation, we would have bracket -4, comma -1, parentheses, union, parentheses, -1 to infinity. Okay. And we now have our solution written in words, written as a solution set, and written in interval notation. Okay. So in the previous example, because -4 is a 0 of odd multiplicity, meaning that its factor x plus 4 is raised to the first power, the sign of f changes on either side of -4. However, because -1 is a 0 of even multiplicity, because its factor x plus 1 has a power of 2, so a second power, the sign of f does not change from one side of -1 to the other. Okay. So in summary, here are your steps for solving polynomial and rational inequalities algebraically. For step 1, you want to write the inequality so that the polynomial and the rational function is on the left side and 0 is on the right side in one of the following forms. So f of x is greater than 0, f of x is greater than or equal to 0, f of x is less than 0, or f of x is less than or equal to 0. For rational functions, you want to make sure that the left side is written as a single quotient, and you want to find the domain of f because you know that there's going to be some restrictions with the denominator not equaling 0. So for step 2, you want to determine the real zeros at which f of x equals 0. And if the function is rational, then you also want to find the real zeros at which the function f is undefined. And it's going to be very similar to you finding the domain because they're connected. Step 3, you're going to use the numbers you found in step 2 to divide the real number line into intervals. So you want to take your real zeros and the undefined value zeros as well to create your interval, because you want to identify what your graph is going to look like in between each of those intervals. And then for step 4, you want to select a number in each interval and evaluate f at that number. So if the value of f is positive, then you know f of x is greater than 0 for all the numbers in that interval. If the value of f is negative, then f of x is less than 0 for all of the numbers in that specific interval. And if the inequality is not strict, so greater than or equal to or less than or equal to, then you want to include the solutions of f of x equals 0 that are in the domain of f in your solution set. So be careful to exclude values of f where f is undefined. All right, so that is our summary for solving polynomial and rational inequalities. All right, well, that concludes section 3.7.